Apply machine learning to healthcare data, and you'll find predicting type 2 diabetes is a highly saturated field. Throwing generic algorithms at standard clinical datasets usually generates redundant results. To build a valid master's-level project, we must filter that noise into a highly structured, specific inquiry. Training a model strictly on age, body mass index, and glucose levels repeats what thousands of papers have already established. We already know those physiological and demographic factors correlate with diabetes. A new approach requires looking at data outside the traditional clinical lens. The actual gap in the literature lies in the behavioral and psychological periphery. This project targets the intersection of mental health indicators and lifestyle variables, a relationship that is far less consistently explored in current models. Precision starts with the title. Redacting phrases like future diabetes prediction prevents methodological overreach. The approved title defines the exact scope. Explainable machine learning-based type 2 diabetes risk classification using lifestyle and mental health indicators from public health survey data. This semantic shift from prediction to risk classification is mandatory. Unless you are working with a longitudinal dataset that follows specific patients over time, you cannot claim to predict the future. Cross-sectional survey data only provides a snapshot in time. Scoping the project with this level of precision on day one establishes the boundaries of the analysis and dictates the scientific validity of the entire 6-month endeavor. Moving from purely physiological diagnostics to holistic epidemiology changes the core of the research. This requires extracting very specific psychological indicators from the dataset, self-reported metrics on clinical depression, frequency of poor mental health days, chronic sleep problems, stress levels, and overall psychological well-being. These psychological metrics sit alongside standard lifestyle variables like diet, smoking, and exercise. The novelty of the project relies on mapping how their combined interaction influences metabolic health. To map those interactions, raw accuracy is insufficient. The model requires explainable AI, allowing us to understand the specific logic the algorithm uses to reach a classification. We are moving towards explanatory models, designed to offer tangible screening support for complex public health intersections. Your choice of dataset is the first critical failure point. You cannot use the Pima Indian diabetes dataset. Its small sample size, extreme overuse, and complete lack of mental health variables make it unsuitable for this research. Instead, you will choose between two major public health surveys, the CDC's BRFSS dataset or the NHANES dataset. The BRFSS dataset offers a streamlined path. The data is clean and manageable, though mental health measures are basic. NHANES provides a stronger scientific foundation. It contains nuanced indicators for sleep and depression, essential for robust mental health analysis. However, NHANES requires rigorous data merging across multiple cycles. The pre-processing pipeline is significantly more demanding. Regardless of the source, your pre-processing must firmly define the target outcome, specifying whether you are performing a binary classification or a multi-class approach that includes prediabetes. Dataset selection sets the ceiling for the project's scientific value. Targeted pre-processing yields deeper epidemiological insights. Once the data is curated and the target outcome is locked, the pipeline moves to the algorithmic phase, focusing strictly on risk classification. You will construct and compare logistic regression, random forest, XGBoost, support vector machines, and k-nearest neighbors. Logistic regression serves as the necessary baseline. It provides a benchmark to determine if the complex, nonlinear architecture of tree-based algorithms actually provides a performance advantage. Raw accuracy is a deceptive metric in public health. Since health survey data is often imbalanced, a model can appear accurate simply by defaulting to the majority healthy class. We counter this with a comprehensive evaluation suite. You will track precision, recall, and the F1 score, then map out receiver operating characteristic curves to directly compare the area under the curve for each algorithm. This statistical evaluation must be paired with a confusion matrix. You need to see the exact volume of false positives against false negatives to contextualize where the algorithm fails. In diabetes screening, the public health cost of a false negative, missing a person at risk, is fundamentally different than a false positive. Many researchers stop at internal validation and fail to extract any actual public health meaning from their models. We will use SHAP and LIME to pry open the black box architectures of models like XGBoost, revealing the mechanics behind the risk scores. A SHAP summary plot provides a global explanation. The y-axis ranks variables by predictive weight, and the x-axis shows their impact, color-coded by feature value. Isolating poor mental health days reveals how high values push the model toward a positive risk classification. You will apply this same logic at the micro level, generating local SHAP explanations for 3 to 5 individual patient cases. Mapping these unique interactions demonstrates the model's utility as a theoretical screening tool for clinicians managing individual patient cases. Explainability transforms mathematical predictions into actionable, transparent epidemiological insights. No coding begins until the architecture of the project is formalized. You will submit a 2-page concept note for approval before starting your data analysis. This document must contain your finalized title, the exact dataset link, and a variable breakdown, along with a literature review of 10 recent papers and a tightly defined research gap. The concept note commits you to your final deliverables: the model comparison table, the ROC curves, and the SHAP summary plots. You are required to dedicate specific sections in your final report to the research gap statement and the model's limitations. Documenting all these steps prevents algorithmic wandering and keeps the project within its 6-month deadline. Finally, we must establish the boundaries of your academic claims. Overclaiming AI capabilities is a significant scientific error. Remember, your algorithm does not diagnose diabetes, and it does not predict future health outcomes. Avoid causal language. Finding a mathematical correlation does not mean mental health causes diabetes. Instead, use precise academic terminology: screening support, risk classification, and association-based prediction. Your final discussion must focus on public health relevance, inherent survey data biases, and the ethical concerns of using mental health indicators in automated screening. Achieving true postgraduate mastery of data science rests on the honesty, precision, and ethical boundaries of your scientific claims.